Hey everyone, this is a video to go over empirical and molecular formulas, how to calculate them from data. This is basically an application of stoichiometry where prior to this we've always used a formula to find the mole-to-mole ratio, and here we're doing the reverse. We're going to determine a mole-to-mole ratio, and that's going to tell us the formula. Briefly, a little bit of vocabulary first. The empirical formula is always the lowest whole number ratio of atoms. So it's the lowest whole number ratio of atoms. Whereas the molecular formula is the actual number of atoms. And the example I like of this is glucose. So glucose is C6H12O6. That is its molecular formula because that's how many atoms are actually in the molecule. It's a 5-membered ring of carbon with another carbon hanging off somewhere. Then there's a bunch of oxygens and hydrogens. All right, you'll learn about it in biology. So but if we divide all of these subscripts here by 6, we get the empirical formula. That would be CH2O. That's the lowest whole number ratio of atoms, 1 to 2 to 1. All right. So because 6 to 12 to 6 is the same as 1 to 2 to 1. So this then is the empirical formula. And that's normally the first thing we're going to find when we do these calculations. So let's work an example to see what all of this actually means. So we're given determine the empirical formula of a compound found to contain 0.789 grams of carbon and 0.202 grams of hydrogen. The first thing we're always going to do is we're going to convert grams to moles, which should not surprise you, as that's kind of always our first step in pretty much any stoichiometry problem. So we go to the periodic table. There's 12.01 grams of carbon in 1 mole of carbon. And there's 1.01 grams of hydrogen in 1 mole of hydrogen. We get out our calculator, and we do these. So 0.789 divided by 12.01. Oops. I don't know how to use my calculator. 0.789 divided by 12.01 is 0.0657 moles of carbon. And then 0.202 divided by 1.01 is 0.200 moles of hydrogen. So now that we're in moles, we have to find the lowest whole number ratio between these. And there's a simple math trick for that. Whichever value is smallest, which in this case happens to be this guy here. Whichever value is smallest of the number of moles, we divide that into all the rest. So here there's only 2 of them, so we just divide both of them by 0.0657, which for the carbon is easy because that's just 1. For the hydrogen, if you punch that in, that comes out to 3. It's like 3 and a little change. It's 3.04, but we can round that safely to 3. All right. So that means that there's a 3 to 1 ratio of carbon to hydrogen. So normally we write the carbon first, so that means that the empirical formula would be CH3. All right. So that's the empirical formula of our compound is CH3 because the mole-to-mole ratio is 1 to 3. All right. Now, here's a follow-up question. If the molar mass of the compound in the preceding problem is approximately 30 grams per mole, what is the molecular formula of the compound? The way we do this is there's a simple formula, which is that we take the molar mass of the real compound and we divide it by the molar mass of the empirical formula. All right. So our empirical formula from the previous part of this was CH3, right? So its molar mass would be 12. Well, we're going to round and just do 12 plus 3 times 1. So that would be 15. So in our formula here, we take 30 and we divide it by 15, and that gives us 2. This is what we refer to as the multiplier for our subscripts to get the molecular formula. In other words, I like to write it like this, like here's CH3, and we're going to multiply all of these by 2. That's my multiplier that I just found by dividing the real molar mass by the empirical formula molar mass. That comes out to be C2H6. So in the actual molecule we're dealing with has 2 carbons and 6 hydrogens, right? So that's what the actual molecule would look like, because that's the molecular formula of the compound, okay? Instead of the empirical formula, which is just the lowest whole number ratio, all right? So I've given you a practice problem here. So grab a piece of paper, work the problem, pause the video, not in that order. Probably you want to pause the video first. And work the problem and then restart the video, and I'm going to work the solution. Okay, so here's the solution. So we're going to, oh, I should have mentioned this to you, and you're probably stuck right from the beginning. I'm so sorry. Whenever you're given percentages like here, what we do is that these are percentages of mass. So what we do is we assume that we have, or pretend, whichever one you prefer to think of it, we have 100%, good God, 100 grams of the substance, all right? That would then mean we would have 87.4 grams of nitrogen and 12.6 grams of hydrogen, all right? You do that by assuming or pretending you have 100 grams of the substance, all right? That just changes the percentages to grams, and now you're off to the races. So, all right, if you could not solve it up to this point because of that, pause it here and then come back and watch it. All right, so we go to the periodic table, we get the molar mass for nitrogen, we get the molar mass for hydrogen, which I'm guessing by now you have most of these memorized. All right, so now we get out our calculators. 87.4 divided by 14.01 is 6.4 moles of nitrogen. Notice that I keep labeling these by the unit and the substance because I'm trying to keep track. If you don't keep track of your moles, you often are going to get them flipped around, and you're going to be confused about which one you have, which one corresponds to which number, and it gets real confusing. So just try to keep those straight. We have that many moles of hydrogen, and then we divide by the smaller one, which is the nitrogen, and that's going to be 1, and that's going to be 2. All right, so our empirical formula then is going to be NH2. If it makes you happy to write the 1 there for the N, go right ahead, but if it bothers you or you don't like it, it's just as good, if not better, without the 1. Okay, so that's our empirical formula. All right, now to find the what is this? Molecular formula, we need the molar mass, the real molar mass, and I think I'm going to try to squeeze this in here because I'd like to keep it all on one page here. So we're going to move this guy up just a little bit. Gives ourselves a little bit of working room. So for the molecular formula, we're going to take the real molar mass, which is we're given as 48, and then we're going to find the molar mass of this guy. That's 14 plus 2, so that's 16, if I did that in my head. Okay, so now that gives us 3. So our multiplier is 3. So our empirical formula is NH2. But we're going to multiply all of those by those subscripts by 3, and that's going to give us N3H6. So that is our molecular formula for this compound. I made this compound up for this problem. I'm pretty sure it doesn't really exist. If it did, it would be really unstable. But anyway, so so this is going to be our molecular formula. Okay. So just one more time, the way you solve these is you take, in the case of percentages, you assume 100 grams. So that gives you that many grams of each of them. You change grams into moles. That gives you the number of moles. And then you divide by the smallest value. and that gives you, that is how you get that into a ratio. Here the ratio is 1 to 2. So our empirical formula is NH2. Notice that the 1 goes with the N, and that's why I kept writing that down. And then to get the molecular formula, we take the real molar mass, we divide it by the empirical formula's molar mass, that gives us a multiplier. We multiply the subscripts, and that gives us the molecular formula. All right, hope this was helpful. Feel free to leave me a question in the comments and or get in touch with me. And thanks for watching.